Thank you very much. So my idea was to talk about complex cells, which is a topic that I like very much. And because of this venue and the way this all works, my approach is going to be much more low level and relaxed and intuitive. And there are two possibilities for the outcome. Either everyone will enjoy themselves, or both the group of mathematicians and the group of physicists will equally feel uncomfortable. So kind of, let's hope it's for the first one. I want to begin with a few remarks just to kind of connect this topic to the previous talk. Now, the theory of complex cells, which is developed by Binyamini and Novikov, which from now on I will say Gal and Dimitri, since they're both here. So it's kind of a pretty thick paper. There's a lot of aspects to this theory, so we will just choose one possible pathway to understanding what's going on. And okay, so yes, and also I will try to say the word information a lot of times. Okay, so so we had these sharply definable sets, and we had this motto that a set of the format and degree of the set somehow control the complexity, the amount of information the set contains. And the way this was formalized was via the axioms. It was kind of, you have a set of format f and degree d, and you start playing with it, experimenting with it. You take a union of your set with some other things, with some algebraic hypersurfaces. And at the end, you project it all to a line. You can count the connected components. So that's like the result of the experiment. And the assertion is that you're not going to get more. So the answer at the end is not going to be more complicated than the sets you started with, and the complexity of the experiment itself. You saw that these Boolean operations and so on, they kind of increase the degree. So that's one way to say that, you know, that f and d quantify the amount of information in your set. Another way to say is that the set is just made out of poly fd bits, like geometric bits. And this is very important in o-minimality. So these are called o-minimal cells. And in dimension 2, there are 4 types of o-minimal cells. There's a point, there's a vertical interval, there's a graph of a function, and then there's the area between the graphs of 2 functions over, say, an open interval here. And every o-minimal cell set is a finite union of these cells. And the following thing is not exactly correct, but it's more or less correct, that a set of format f and degree d will be a union of poly fd such cells. And a nice way to think about a cell like this, for example, the 2-dimensional example we have, is it's canonically a unit of a square. So if you have like a 2-dimensional cell like this, you can parameterize it by a square with a triangular type map. So, I mean, first you parameterize this x part, and then once you fix x, you use this vertical to parameterize the vertical between these 2 functions. So something like this. Okay, so these cells are kind of the basic geometric bits, but not all cells are the same. You could have a cell that looks, I don't know, kind of simple, and you could have a cell that looks very complicated. So what you could do, you could say, all right, let me try to insist that my cells actually contain small amount of C1 information. That would amount to saying that if you parameterize your cell by this square, then these functions should be C1 smooth and with bounded C1 norm. So let's say I don't want to use bad cells. I only insist on using these good C1 cells. Well, then the answer would still be the same. A set of format f and degree d is a union of poly fd such good C1 cells. Also with C2 and with C3 and so on. But the point is that the amount of these cells you need grows with the order of regularity of their cells. So if I want the cell to be CR smooth with bounded CR norm, and I take R to infinity, I will actually get an infinite amount of cells. So kind of this tells us, this hints that not all the information contained in a definable set is actually bounded by its format and degree. If this information can be somehow measured with C1 structure or C2 structure, then it is true. For example, if you have I don't know, a curve inside your unit square and it has format f and degree d, then its length will be bounded by poly fd. This is true. And okay, but some things are not, some information cannot be captured like this. And to do this, we actually have to take this R to infinity, we have to enter the analytic world. If we just use the CR world for a fixed R, then everything is still kind of uniform. And I should say that the question of how many good CR cells do we need as R grows to infinity, this analysis is a key point in the point counting result. So it's important for that. And okay, so now we're in the complex analytic world. And what is like a good cell? What is like a good holomorphic map? A good C1 map is a map whose C1 norm is bounded. But I claim that, I mean, it's more or less an example. How I write it down, yes. So let's say we have a map, a holomorphic map, that is defined on the disk of radius 2. And let's say it's bounded. I like to say that it's bounded by 2, but it may seem unnatural, but I prefer to say it like this. The holomorphic. Then the restriction of F to the disk of radius 1 is, controlled or good, or, contains a finite amount of analytic information. You should think about this. If you want, you can think about it quite easily, that you have this disk of radius 1 and your disk of radius 2. And if you know that your function is defined on the disk of radius 2 and is bounded there, then you can actually bound, say, all the derivatives inside the disk of radius 1. Because of Cauchy's formula, right? You take a point even near the boundary, you can evaluate the derivative using an integral over a fixed line. And if you did not have this extension property, if you're trying to understand what's going on in the boundary, you would have to use a very, very, very small integration path. You would get nothing. That's just some intuition. And the basic, okay, so if this is a basic unit of kind of analytic information, the question is, say we now have an analytic space, a holomorphic manifold. By the way, we'll be talking mostly about dimension 1 today. So a Riemann surface, for example, how many such maps do you need to cover this Riemann surface? And is that going to only depend on the degree? If this Riemann surface is given by some algebraic equation, is that number only going to depend on that degree? And the answer is no. And no, it will not depend only on the degree. But before we do that, I have to recall a few facts from complex analysis that will help us. First fact, if you have a function from a unit disk to itself, unit disk is like the hyperbolic plane, then it is distance decreasing in the hyperbolic metric. So this is known as the Schwarz lemma or something like this. Usually in a basic course, it's stated like this, that if f of 0 is 0, then f of z is smaller than z. That's how it's stated. And if you compose this inequality with some isometry of the hyperbolic plane, you will get exactly that f is a distance decreasing. The second fact, so that's one phenomena from complex geometry. The second fact, it's called Cobbe's quarter theorem. So now you say that you have an injective holomorphic function, then actually that maps 0 to 0, then actually the image must contain some kind of ball around 0. And I don't want you to think about this kind of formulation. I just want you to have in your minds the following picture, that a holomorphic map cannot squeeze your disk too much. It cannot be distorted. So kind of this, right, is impossible for a holomorphic map to do. And the reality is that if you try to distort the holomorphic map in one direction, it will actually have to rotate. The reality looks like this. If you try to make it thin in one direction, it would have to rotate. And once it's thin enough, maybe like this, once it's thin enough, it's going to intersect itself and no longer be injective. This is kind of the phenomenon. This is the intuition I want you to have in mind. Okay, so that's just the local thing for the hyperbolic plane. Another thing, so let S be a connected Riemann surface, not necessarily compact, and suppose that the universal cover is the hyperbolic plane. Now look, the universal cover, it has a canonical complex structure, and it's simply connected, so it can be one of three things. It can be the Riemann sphere, it can be the plane, C, or it can be the hyperbolic plane. These are the only simply connected Riemann surfaces, and generically, almost always, the universal cover will be the hyperbolic plane. And the cool fact is that if this is the case, S will be called hyperbolic. S gets the hyperbolic metric from its universal cover. This might be somewhat surprising. Metrics are usually pulled back, not pushed forward. But this actually follows from fact A quite nicely, right? You have S, you have a point in S, the fiber above it. You are kind of, you're not sure from which point in the fiber you're going to take the metric. It doesn't matter because all the deck transformations are going to be isometries. Okay, but anyway, yeah, and okay, and also if you have a holomorphic map between two Riemann, hyperbolic Riemann surfaces, then it will also be distance decreasing. So all of this is on the level of an exercise. And the last fact I need, the first one is very not easy, the second one is somewhat not easy. Any compact Riemann surface of genus greater or equal to 2 is hyperbolic. Okay, so you have Riemann sphere, tori, elliptic curves, and then everything else is hyperbolic. And another thing is that if you have a domain that does not contain at least 2 points, then it's also hyperbolic. And this follows from Picard's theorem, right? The universal cover of this, it can't be the Riemann sphere, because that's compact. And it can't be C, because that would mean you have an entire function missing out on 2 points. That's impossible. So it has to be hyperbolic. All right. Any questions? Please feel free to ask me. All right. Perfect. So let's consider the following example. So let's try to take some kind of analytic set and see what happens when we try to cover it by such maps. So let's denote x epsilon 2 to be the hyperbola xy equals epsilon, where x and y are smaller than 2, and x epsilon 1 is going to be the same hyperbola, but x and y will be smaller or equal to 1. And the correct way to ask this question is the following. So I guess, what is the minimal, something like this, the minimal size of a collection F1 up to Fn of holomorphic maps from the disk of radius 2 to this hyperbola, but they are bounded by 2, such that the union of this thing contains x epsilon 1. So I'm trying to cover x epsilon 1 with maps from the unit disk, but I insist that these holomorphic maps actually extend to a larger disk and are bounded there. And and let me just give you the answer immediately. The answer is that n is at least asymptotically log epsilon. Okay, this is already kind of the answer to our questions, because for any epsilon, this set is just an algebraic set of, I don't know, degree 2 and format 4, I think, because it's in C squared. So, I mean, the fact that the answer depends on epsilon is disheartening. Okay? And in fact, if you do try to do it with this many maps, you will get very, very bad maps. No, you won't get maps that are reasonably thought of as parametrizing maps. Okay, if one insists, say, on fi being, let's say, 1-to-1, so like it sounds more like a parametrizing function, then you actually need exponentially more disks. And let me tell you something that kind of, the goal is not to cover your Riemann surface with a disk. If you want to do that, you can just look at the universal cover. That's one map from a disk to the Riemann surface that covers it entirely. The point is that these disks, you want them to be well controlled. They have to be small in a certain analytic sense. And let's explain what is happening here. So to understand this, we have to note that these, I mean, we write them like this to show that they're actually algebraic of degree. Yes?
Is that bound sharp?
Yes. Yeah, so these ellipses are actually biholomorphic to annuli. So let's say what happens when you take x epsilon 1 and you project it down on the x-axis, right? So y can be at most 1, which means that x has to be at least epsilon. And that's it. And for any x between epsilon and 1, you can just, the inverse image y is given by epsilon over x. So it's going to be an annulus like this, a of epsilon 1. By this I mean just the set of points, maybe x is better here, that are between epsilon and 1 in norm. And if you project this second thing, it's a similar thing, right? Y is at most 2, so x is at least epsilon over 2. Yeah. And the key point is that this thing, and this is a biholomorphism, so completely the same thing, but this thing is hyperbolic, right? Because it's a domain that's missing out on 2 points and even many more. And now the key point is that the diameter of, take any one of these disks, the diameter of the image of a disk, but with respect to the hyperbolic metric of this domain, okay? So I will be writing it like this. Because f is distance decreasing, it cannot be larger than the diameter of the disk of radius 1 inside the hyperbolic metric of a disk of radius 2, right? I mean, you have a map from the disk of radius 2 to x epsilon 2. These are two hyperbolic Riemann surfaces. And yeah, so they're distance decreasing. And now I take some small compact bounded set d of 1 inside here. The image must also have bounded diameter. And this is some number c. Okay, so this is the key point. This hyperbolic stuff really tells us that the image of the disk is small. And now, what is the geometry here? I mean, what is the diameter of this thing with respect to the hyperbolic metric of this thing? The answer is log epsilon, all right? I will draw a nice picture soon, but the answer is log epsilon. So what's happening is that you're trying to cover a set that is log epsilon long with sets that have bounded diameter. So of course, you're going to need at least log epsilon sets just to cover the distance. But actually, there are a few more phenomena here. So let's draw this picture. So I have this kind of unbounded annulus. This entire annulus is a of epsilon over 2, 2 in its hyperbolic metric. And the boundary, the metric explodes near the boundary. So kind of when I draw it like this, these two boundary parts are going away to infinity. They're far away. And within this thing, there is a subannulus. So this annulus is going to be, a of epsilon 1. And it has the following 3 interesting features. First feature, which I already mentioned, is that the diameter here is log epsilon. Second feature is that these two boundary circles, these are just these two circles are the boundary of this annulus in here. So these two circles are of constant length. So as epsilon goes to 0, they stay exactly the same, actually. That's the second feature. And the third feature is that it gets pinched in the middle. This length goes to 0. All right. And so actually now if we think, okay, what if we actually try to cover this red annulus with log epsilon disks? Well, every disk will have to take at least a constant step. We start here and we go all the way here. Every disk will have to take at least a constant step towards the other end. And because of this Kobe stuff, I didn't write Kobe, but because of this non-distortion principle, as the annulus gets thinner in the middle, the disk will have to wrap itself around the annulus many times because you can't make it go here. So maybe in the beginning you have a disk that goes a constant length and it looks reasonable, but as this is very, very, very short, because of this Kobe stuff, the disk will have to, I don't even know how to draw this, wrap itself around this thing. And in fact, as epsilon goes to 0, it would have to wrap itself around this thing more and more and more and more. And so I mentioned here that if you try to do it with this many disks, the maps are not going to be one-to-one. Actually, far from it, as epsilon goes to 0, the size of the fiber goes to infinity. This disk will wrap itself around this thin part more and more and more times. So that's kind of bad. What you can actually do is make the disks smaller as they approach this thin part so that they don't wrap themselves around this. And then you can get that Fi is one-to-one, but you will have to have more disks. Okay, any questions or comments or remarks? Perfect. So what did we explain here? We just explained that you can't expect to do it with a uniform number of disks, with a number of disks that depends only on the degree of what you started with. And what's the key takeaway here? I have space here. So what is the kind of lesson? So the lesson is that one should allow, when you're trying to cover or parameterize your complex set with basic bits, one should allow maps from an annulus also, and not only from a disk, let's say from a large annulus to, I don't know, your space, whatever, C or some Riemann surface X, in addition to f of A, f from D to X. So similarly to annuli, if your holomorphic function extends to the annulus that's twice as large, similarly to disks, excuse me, and is bounded there, then the behavior of f, I mean, this kind of means that f restricted to this annulus is good. And just, you know, so what happens here? I'm telling you that, okay, if you're trying to cover an annulus, then you will have to have many disks. And then I'm telling you, okay, if you allow me to cover with annuli, I can just do it with one basic bit. So that's maybe not impressive because it's just an annulus. But the point is that that's actually enough for everything. So, and in fact, let's say it like this.
I have a question.
Yes.
So I'm not sure I understand precisely the motivation. Why do you want to extend it to radius 2? You could imagine to extend it to radius 1 plus epsilon.
That's an excellent question. So if you extend it, so say your complex space is actually this annulus. If you extend it, if you say that you want a map from a disk with a very small extensions, it's like saying that you are parametrizing this annulus by one large blob of a disk. But that's actually not the phenomena in complex geometry. The phenomena is that as something goes long hyperbolically, it only becomes long in one direction, and the other direction it's thin. So it's kind of overkill, quote unquote, to try and parameterize it with huge disks. That could be a possible answer. Okay, so in fact, xy epsilon can be replaced by just any equation, say polynomial equation, and one can achieve this cover, which is called the cellular cover, this cellular cover with poly degree P disks and annuli. So the idea is kind of simple, right? A set of format F and degree D can have a large hyperbolic metric. And so I am kind of replacing my basic bits with bits that contain a lot of information actually on the one hand, but on the other hand are still well controlled in a uniform sense that I will mention later. Okay. Perfect. All right.
If you go to higher dimension, what kind of cells do you fit?
That's exactly the next point. So in dimension 1, this theory is kind of, people understand dimension 1 quite well, but to me, a very important aspect of this theory of cells is that it's multidimensional. And I'm not even going to define precisely or rigorously what are these multidimensional cells. I'll just give us some examples. But before this, so kind of complex cells in dimension one. So we said that, so actually there are some possibilities. It could be just a point. It could be a disk. It's always centered at 0. Could be a punctured disk, which for this discussion, we didn't really need punctured disks because we were mapping to a compact surface. And I mean, if you have a map from a punctured disk to a compact surface, it will extend to the singularity because of Riemann's removable singularity theorem. So in this setup, we didn't need them, but they are important for the theory. And an annulus. A of, say, R1. So these are the basic complex cells in dimension 1. And they have an extension. So we use let's take a number larger than 0 and smaller than 1. You can consider this extension. So in the case of a point, it's just still going to be a point. In the case of a disk, it's going to be a disk with a larger radius. I'm really sorry that the delta is smaller than 1. And I'm sorry, that's the way it works. In this case, it's going to be this disk, and in this case, it's going to be an annulus whose inner radius becomes smaller, but their outer radius becomes big. So before we only talked about delta equals to 1/2, but there is an entire quantitative aspect here. So kind of the more your cell extends, the better your function is on the original cell. And I want to say that these extensions are normalized. Where is this? Where am I? Never mind. There was okay, I actually remember. So there is a notion of a row extension. What is a row extension? It's the delta extension for a delta satisfying the following equation. Oh, I really hope. Really, I can't find it in my notes. If C is D, it's going to be pi squared divided by 2 log delta. If C is of type puncture disk or annulus, the exact formula doesn't really matter. The point is the following fact that, so if S is a component of a boundary of a cell, then the length of S, of this component, with respect to the metric of the extended cell, is at most rho. Also kind of, the more you extend the cell, the smaller the length of the boundary becomes. Okay, and let me just give you 2 examples of higher dimensional cells, just that you get a feel how it's going to work. Yeah, so we can consider, for example, this cell, which is denoted like this. So puncture disk of radius 1, and then an annulus of radius x and 2I, outer radius 2I. So first of all, I will just write out precisely what this set is. So x is allowed to vary in a puncture disk of radius 1, but then y is allowed to vary in an annulus whose inner radius is x and the outer radius is 2. This is kind of I deleted this, but this is, the logic here is kind of similar to real cells, where if you had a cell which is the area between 2 graphs, then x can belong to some interval, and y will be bounded by 2 functions of x. Okay. And yes, okay. And you can extend this cell. You can consider this delta extension. You can extend just the first coordinate. If this is C, then the way C delta will look like is this thing, but there's some caveat here about extensions that actually we want this original fiber to be defined as is over the extension of the base. I mean, in order for this thing to make sense, we want x to be smaller than 2 whenever x belongs to this base. And so actually, this is possible only if delta is larger than 1/2. And this is typical that you can only extend a cell up to a certain place. And there's another nice cell. And the reason why it's 2i and not 2, it's because it's a complex theory. And for example, here, I can plug any complex number in this base for x, and I will get just a constant one-dimensional cell for y. So that's why kind of complex numbers. Another interesting cell is the following one. Just kind of having some fun. Don't know why it's d0, just a, x squared, y plus 2, 12. I don't know. The point of this cell, it's very easy. X is between 1/2 and 2, y smaller than 1, z is between 12 and this thing. Point being is that this x squared, y plus 2, it gets to be 12, right? I mean, near the boundary of the base. So if x is 2 and y is 1, I believe this is 12. And this means that this cell has no extension at all. Okay. And one can use different deltas for different coordinates. So C rho is also defined. So what I mean here is that this renormalization between delta and rho, it depends on the type of your cell. So kind of if I want to take this cell and take its rho extension, I would have to delta extend the base according to the correct delta. In this case, it's a puncture disk and annuli, so it's the same. But generally speaking, every single kind of coordinate can be a different cell, and you might need different delta extensions. And to me, I want to now mention one of the main results of this theory, which to me is quite surprising. So this is due to Gan and Dimitri. And I'm not even writing the whole quantitative aspect of this theorem, just the qualitative aspect of it. So let's say that C is a cell that admits a rho extension, and F is a map, holomorphic map, defined on the extension, and it maps into some Riemann surface. And for now, I will just take this Riemann surface, just C without 0, 1, which is also hyperbolic, holomorphic, and bounded. Then one of the following holds. Either f of c has small hyperbolic diameter, or maybe f of c is constant, is near 0, 1, or infinity. Right, so
it bounded there?
Hmm?
You need bounded there?
You need bounded. I mean, you wrote bounded. Yeah, I'm not sure if you need that actually. I don't know. Wait, no. I mean, okay. For this case, probably it's not really logical to say that f is bounded. Yeah. Okay, so I mean, okay. If you're small hyperbolic diameter and small hyperbolic diameter, if you're near 0, 1, or infinity, then you don't have small hyperbolic diameter, but you are actually Euclideally small in real life. And the point is that you control f on C, by the way, right? That's the logic of this entire thing, that f is defined on C rho, but you get to control f on C. F is controlled on C. And why do I think that this result is very nice? Because it's not like the one-dimensional case. It's not as if C rho has some kind of hyperbolic metric, and C within C rho has some kind of diameter, and it's a holomorphic map, and so you get that the image has small diameter. That's not the case. There is no kind of hyperbolic structure for this thing. It's really a cell that coordinate-wise admits this rho extension. And from this, you get a result that is kind of global on the entire cell. I think that's surprising and interesting. Any questions? Perfect. So now let me state like a baby version of the main result of this paper, which is the cellular parametrization theorem, and not even sketch the proof, but I will say a few words on the proof. How do I, yeah. So maybe like this, theorem. So I want to do it the simplest way possible. So let's say that F is defined on the polydisk of radius 2 in CL. I know it's a, let's say it's even an algebraic or a polynomial. You can think of it, algebraic function, I mean, it's just a function that is a root of a polynomial. But if you want, you can just consider this to be a polynomial. Algebraic function of complexity beta, or you can think about this as a map definable in a sharply o-minimal structure with format f and degree d. That's also possible. Then there exists, and fix rho, fix some kind of rho. Then there exists a collection. So I'm really giving you a much weaker version than the true main result, but still something that you can understand this. So you have a collection of maps from cells with a rho extension to this polydisk. So they are bounded by 2 of size. So poly L. L is the kind of number of variables in the story. In the sharp case, you will have format here. Of what? Of beta and rho, or 1 over rho, probably, if rho is 0, yeah, so probably rho, such that. And I'm always saying nothing. I will just say that maybe one C, I will write it down and then explain what I mean, are algebraic of complexity beta. So you started with an algebraic equation, you're getting cells that are also algebraic. 2, the union of fj's of C covers the disk, the polydisk of radius 1. And the third thing, for every j, I mean f of fj is either just 0 or non-equal to 0 everywhere. So, I mean, we are covering the entire polydisk of radius 1 with cells, but we make sure that some of our cells will cover the 0 set of this equation. Some of our cells will hit completely in the complement. Okay, this is kind of a main result, and I want to say a word on the proof before I continue, because there's some very nice mathematics going into the proof. Just kind of to build up intuition of what is happening here and why do we need annuli for this result? Let me say something about this rho here. So you see that kind of as rho goes to infinity, probably, yeah, delta goes to 1. So that makes no sense to me. I'm confused. I think it's 1 over rho. Right? So when rho is very close to 0, this extension is very large. So the maps are very well behaved on CJ, but you can't get it for free. You will need more maps. Yeah, 1 over rho. Thank you. Okay, just a word on the proof. You can imagine that you have here a c-axis, and here some kind of CL minus 1 axis. And okay, everything is inside the polydisk of radius 2, but imagine it to be kind of huge, okay, outside of the margins of the board. And you have this set, some kind of set, f equals to 0. Okay, and there is some kind of low-dimensional set in the base where this projection is bad. Let's say it's ramified or just bad, okay? And you handle this low-dimensional set by induction. And let's say if you have a cell here, let's just say that above it you have exactly, I don't know, exactly d points on your equation, on your hypersurface. And these points, let's say that they vary holomorphically on this small set here. That's what it's meant to be good. Let's call this y1 up to yd. of Z, where Z is some point here. And let's first fix this. Okay, we have a cell in the complement, right? We use induction on the base to cover both the bad set and its complement with cells, just like this thing. And okay, let's just think of one fixed Z for a moment. This projection, let's call it pi, and let's draw pi inverse of Z. What do we see in this pi inverse of Z, which is living inside, not exactly a plane, inside the disk of radius 2, which is huge, okay? You will have these points, y1 up to yd. There are some kind of points. And now what you're supposed to do, you're supposed to cover both these points and their complements. Covering this point with a cell, it's like, you know, you cover this cell and then the last coordinate is completely determined by the base. So that's relatively simple, but you need this extension thing, right? That actually, yeah, on C rho, right? I think, probably the same. So kind of what I'm saying is that what you want to do, let's call the set sigma. So what you really are interested in doing here is cover C without sigma, or disk of radius 2 without sigma, doesn't matter, with poly beta. So this D, the number of points above a point here, is definitely going to be controlled by the degree of your equation F. By poly B, disks, puncture disks, and annuli. Okay, you will probably, if I do it like this, I will have to write 1 over rho here, whose rho extension does not touch sigma. So now let's forget about rho again. Let's just fix rho to be this fixed 2 extension, because there is also a theorem that any cell can be covered with cells admitting a large extension. So if I can do this with cells that have bad extensions, even if this rho is quite big, if the extension is small, I would be able to cover this cell again with cells with large extensions. So let's just forget about this rho and think about 1/2. We're supposed to cover this plane without these holes with disks, puncture disks that are here to be placed around one of these points in sigma, and annuli. So, you know, and if you place a disk, you want its double extension not to touch sigma, because this entire cell is dedicated to covering the complement of the zeros. And the fact that you can even do this with a number of cells that only depends on sigma is non-trivial, and you actually will need annuli for this. Let me explain to you why. So you could suppose, you could imagine that something like this happens. You have 2 points in sigma that are very, very, very close to each other, and then another point in sigma, which is very far away. Let's say this length is about b, this entire length. And saying I am not allowed to use annuli. So since these 2 points are very close together, I am only allowed to place a very small puncture disk around this point, because I need the 2 extension not to touch this. So already this part is not covered. So I would have to place a disk here, which is allowed to be slightly larger, and so on and so on. And it's an easy computation to show that you need about log b over a disks to achieve this. So kind of the issue of doing it with only disks is that you can have these clusters. You can have points that are close to each other, but far away from other points. And how does an annulus save the day in this type of situation? Basically, if you are allowed an annulus, then kind of here, then I will place an annulus around something like this, which will look something like this. And this annulus now acts as a buffer between this area of the plane and this area of the plane. It already covers a lot of ground, and so kind of this is, I deal with this by induction. Okay, so kind of the point I was trying to make, that this is kind of impossible to achieve with just disk. You really do have to have the annuli. At what time did I start exactly? I started at 11:10, right?
Yeah.
Roughly 11:10. It's 45. Okay. Perfect. Any questions? All right, so I would like to start concluding the talk by just mentioning some features of this theory and some recent work that is kind of maybe more sympathetic to geometers or to physicists like yourselves, because kind of you may feel that I'm using here a lot of this soft analysis and this entire quantitative thing, like the larger the extension is, the better my control and so on. But actually these cells can be also very useful for rigid type situations. So some features / applications. Yes, and I wanted to say another thing, that I basically kind of explained intuitively the induction step, but the same kind of logic works if you want to try and construct a cellular decomposition for just a curve. The same kind of logic is what is needed for the induction base, basically. Yeah. So I had an opportunity to give you the same picture earlier, but with a different context. But I think like this is more understandable. All right, so kind of, so they are fantastic, right? That's definitely a feature. Okay. Second feature, okay, so original, let's say, applications in dynamics. So at the very start, so this is just the, I mean, in this original paper, there are several directions in which the authors present here are taking these cells. One of the more prominent ones is, I mentioned really at the start of the talk that kind of, if I want to cover a definable set or even say an algebraic set with bits of bounded CR information, then the number of bits I will need will grow to infinity with R. And the exact dependence in the algebraic case was given by Binyamini and Novikov using these cells. Okay, that's one thing. So another thing which is very important, kind of the theory of ln, they are, I know if Gal can correct me if it's an unfair statement, but they are the infrastructure, I guess, for ln functions. So the theory of ln functions, it's very important because a lot of functions are ln, basically all the functions more or less, and yeah, and they are kind of investigated, defined, and so on using these complex cells, and a theorem like this fundamental lemma plays a role in that theory. So, okay, so due to more recent work by Odette Kermon, this thing interfaces well with sharp o-minimality. So in the original paper, if you look at the main result, something like here, there were two formulations. One formulation is like I did here, where f is an algebraic function. And before sharp o-minimality, kind of in o-minimality, the finiteness would very often be expressed using families. So, I mean, yes, a definable set has finitely many connected components, a set definable in no minimal structure. But much stronger and still true is that a family of definable sets, if you have a family of definable sets, then there is a uniform bound on the number of connected components for every such set. And yeah, so that was how it was formulated. Either you have a single algebraic function or you have a family in a no minimal, a definable family of equations, and then you try to make a definable family of parametrization with a uniform bound on the number of cells you need. But due to the work of Kermon, you can just do it for any sharply minimal structure. You can assume that you can start with an equation, hypersurface that is definable in a sharply minimal structure, and the cells are going to be definable in the same structure in the sense that their radii, the functions appearing here, are going to be definable in the structure. Yeah.
To have as a property for that sharp o-minimal structure that it's piecewise analytic.
Yeah. It should be generated by analytic functions. Yeah, thank you. Yeah.
I mean, with Kalman, he just formulates it for a given complex cell and holomorphic function. So it's not for every definable set, it's only for sets that are analytic.
Yeah.
If you want
Sure.
every definable set to be like this, then yeah, you need some analytically
Sure.
generated.
In my head, I meant that your equation is analytic, but also definable in a sharply o-minimal structure. Okay, and then some also there is some work of mine that this thing interfaces well with rationality. And really, excuse me, I have some kind of an ADHD thing. I wrote this thing here, but I never explained what I mean. What I mean is that if you start with say a polynomial equation, and you're using cells that are algebraic of complexity beta, I just mean that the functions appearing in the radii of the cells are themselves algebraic of complexity bounded using the initial complexity. What is this rationality thing? It's maybe a little bit hard to explain, but the point is that what if your equation was defined over the rational number? Say it's a polynomial whose coefficients are rational, and they all have bounded height. They're also, let's say this is a rational polynomial. With height h, so just the maximum of the height of the coefficients, and let me denote h, small h is the logarithm of capital H. Then actually, if you want, you can produce a parametrization where everything is also definable over Q. But there is a caveat here. It's not as if you go to the algorithm and you plug in a function that has rational coefficients, you will automatically get rational cells. You have some work to do here. You need to make sure that at each step you are doing what needs to be done with a rational cell. And so there's going to be a price that you're actually going to need a little bit more cells than that. I mean, kind of, you can still do it with this many cells, but you will not be able to say anything about the rationality. And by the way, this is kind of interesting because recall that we saw that to cover this epsilon, we needed this annulus in the sense that was written on the board before. We need kind of log epsilon maps. But if I tell you that epsilon is a rational number of height h, then epsilon must be at least 1 over h, right? So this is a very important inequality in heights, basically. And any non-zero integer is at least 1. Okay, so a number of height h is at least 1 over h. So if I told you that this annulus has some kind of bounded height, then actually you can bound the number of disks needed to bound it, right? So this can be done now with log h disks to cover this annulus. To cover, and I mean, this has some consequences. For example, if you have a Riemann surface that has height h, is definable by equations of height h, then it can be covered by log h such disks. So its hyperbolic diameter is at most log h also, right? So that's a nice interface. Okay, and in the last 8 minutes, I want to just say a few words about an application that might be interesting for you. So kind of, basically we use complex cells to solve the following problem, which is very typical, I think, in this, okay, whatever, let me just say it. So suppose that X is a Riemann surface, large genus, okay, so, and genus G, and you have forms. So a genus G Riemann surface will have exactly G holomorphic independent forms, holomorphic one forms, right? So there is a well-studied map from, and P and X is a base point. There is a well-studied map called the Abel-Jacobi map, which takes X, let me first write, then explain, to CG modulus some lattice. What exactly is happening here? I mean, the map is given by the formula X goes to this vector, integral from P to X omega 1, up to integral from p to x omega g. This is called the Abel-Jacobi map, very important in complex geometry. And okay, it's not well defined because a path from p to x, I don't know if you have an annulus in your Riemann surface. I mean, this is p, this is x. You can go like this. You can maybe go around, and you will catch some residue that will change the value of the integral. So this map is only well defined when you map it to this quotient by a lattice, which is exactly, the lattice is given exactly by the integrals of these forms over an integer cycle. Okay, and so let me do another cover, so it will be, so this is the universal cover of this torus. And inside this universal cover, there is a fundamental, this is a fundamental domain. Just some kind of parallelepiped that, you know, is a fundamental domain for this lattice, quite easy to imagine. And so I want to study this map as a map from x to delta x. Because this is a quotient, I don't want to be messing with that. This thing has kind of coordinates that this map, I want to study this map. And okay, and this map is made out of two parts. I mean, what's the strategy? What's the strategy usually people take when studying such things? Usually they will take a branch cut. So they will cut something away from your curve so that it will be simply connected. So if you have a Riemann surface, it's real two-dimensional, you make a one-dimensional cut, but one real dimensional cut, and you're left with something simply connected. And since this is simply connected, there is a well-defined map from here to here, and it's given by actually the same formula, okay? Clearly. But now this map from here to here, it's just a coordinate map kind of, and it's given by this formula. This is a Pfaffian map, like the function integral from p to x of omega 1. It is a solution of a differential, algebraic differential equation, right? Its derivative is just omega 1, and we know that all kind of, the theory of Riemann surfaces says that all of these forms are necessarily algebraic, and the Riemann surface is necessarily algebraic. So there are like two parts of it. Okay, so this lift, we understand it, because it's just a Pfaffian map. But then you have, excuse me, this is like delta x. Yeah, and then if you try to identify the quotient with delta x, then you also get a map from CG to delta x, but it's like a complicated map. So for example, in the, I don't know, in the case of C modulo z squared, I guess, it's the kind of map that takes every point and finds the unique representative within the fundamental domain of this point. This map, CG to delta x, is not definable, not o-minimal. And that's kind of clear because it has a different formula for every different square in the plane. You can't really define it with a finite formula. So what is going to be happening here is that you have this lattice in CG, so I'm drawing it now. This is CG, you have this lattice. Let's say this is a fundamental parallelepiped, and the image of this thing is going to be a union of finitely many of these fundamental parallelepipeds. I mean, this is the result that this is the main result of this investigation. And that actually means, okay, so this is not definable, but it is definable. It is definable. And it is in fact sharply definable of degree more or less d when restricted to the union of d fundamental domains, let's say. So the point is to study this map as a composition of this Pfaffian lift and then of this map. So the goal would be to show that we only need this map on a part of CG which is small, which is the union of only so many fundamental domains. And kind of the key thing here is that as the curve, and the answer is that the number of fundamental domains we need to cover this yellow blob, the picture of this thing, is independent of x. It's uniform over all x, kind of as x degenerates, which basically means that it's a Riemann surface, so I don't know. It looks maybe there is some kind of annulus, and then there is maybe another annulus. Yeah, but then now I don't know how to draw these things. Like yes, it's supposed to close down. But then there is one very, 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 very long annulus. Let's say it's something like this Riemann surface. This is a very long annulus, which degenerates. The point is that as this Riemann surface will degenerate, both the lattice of periods, this is called the lattice of periods, and the image of this blob will degenerate compatibly. You will see that as this thing gets long, you can calculate that the fundamental domain gets very long in one direction, but also the image of x modulo b is long. And the point is that even if the lattice was not degenerate at all, even if kind of your lattice turns out to look very, very nice, and your blob also looks very, very, very nice, you still have to make a choice of which fundamental domain you're going to be working with. If you're going to be working with a very degenerate fundamental domain, then you're still going to need a lot of them to cover this thing. My point is that to execute this entire analysis, you need to make a choice. You need to make a choice, what is the correct basis of forms to work with, and what is the correct fundamental domain to choose. And I believe I'm out probably, right, of time. Yes, excuse me. Yeah, but the last sentence is that all of these decisions are just dictated by the cellular decomposition. You take a cellular cover in this sense, and all of these questions, kind of the answer is in the cellular cover. You don't need to think more than that. Okay, thank you.